So again, we'll start with that basic premise that I have up on the board there, that when we measure around the outside of a circle, right, the circumference of a circle, we saw it was equal to 2 pi times the number of radiuses, okay? So about 6.28 times r, if we think about it in, the decimal sense, okay? But another way to measure on the outside of a circle is 360 degrees, okay? That also measures the measures around the circle, we'll say. Okay. So in some sense, we can say then that 360 degrees is equal to 2 times pi times the number of radiuses. And we're just going to use, though, the word radians instead for a unit of measure. Okay. So we now have this idea of, an angle on its circle, right? So I could say, like, for example, if I have a circle here with a center right there, okay, I can talk about this number of degrees, okay, or I can talk about some number of radiuses it takes to go around the outside of the circle, okay, like the arc measure there, okay. And so we also said, okay, well then, if 360 degrees goes around the outside, right, and that's 2 pi radians, then 180 degrees, which is half the circle, right, would be half the number of radians, so that's pi radians. Okay, and 90 degrees would be equal to pi over 2 radians. Right, and 45 degrees is pi over 4 radians. You don't need to keep writing the word radians if you don't want to. It's kind of understood. Okay, it's not a label that you need to keep giving. Okay, if you don't see a degree symbol and you're talking about an angle, then that means you're in radians. Okay, so if you don't see a degree symbol, that means you're talking about radians. There is no real radian symbol. Okay, but if you want to write the word radians, you can. All right, so let's see here. What about something like 60 degrees? What would that be in radians? Okay. I did these here, right? We went half and then half and then half, but 60 degrees is not half of any of these. Any ideas about what it would be as a radian measure? 1/3. 1/3? Where'd you get that from? Nowhere? Well, that's a pretty good guess. Right? It's right. So you must not have just guessed. Did you do anything? You know what you did, or you?
No, I just thought about like 90, like that's half, and then that's the fourth, so like 60's kind of in between that.
Okay. Okay. Okay, I see what you're saying there, using your fraction knowledge there. Very good. 60 is like one of those, 90 degrees and 45 degrees, you've used those angles a lot. 60 degrees is also an angle that tends to show up a lot, especially in those special right triangles and stuff like that. That's true. We can also think in terms of fractions, though, too. For example, 180 and 60, right? 60 is what fraction of 180? Or 180 divided by what gives you 60? 3, right? Well, pi divided by 3, pi over 3, right? So then what would 30 degrees be? What radians? Pi over what? Oh, your pattern falls apart there. Which one is, so what'd you say, CJ? You did say something. I thought I heard someone say, you said 6, right? Yeah, 6 is right. Pi over 6. Okay, a couple ways you can think about this, right? What's half of 60? 30. What's half of pi over 3? Well, again, it's half of pi over 3, so then it would be pi over 6, right? Multiply this by 1/2, and you would get pi over 6 there. Okay? Or you can think about it as 180 divided by, what gives you 30? 180 divided by 6 gives you 30. So pi divided by 6, pi over 6. Okay? All right. But of course, this gets, we don't want to have to keep working with all these like crazy fractions and stuff like that. So here's how we're going to be converting between these two things. Okay? If we're going to go degrees to radians, okay? Well, here's what we're going to do. And there's like multiple different ways, and some different teachers teach different ways to do this, but here's how we're going to be converting. Okay, here's how we're going to be converting degrees to radians. Okay, so let's just take a weird degree measure. Let's do like 47 degrees. Okay, we'll just do a weird one first. Okay. Well, you guys may remember this thing called dimensional analysis. Maybe not. Maybe you did it in chemistry. Maybe you did it in Algebra 1. Okay. Maybe you have awful memories of it, and so you've blocked it from your brain. What we're going to do, though, is we're going to use this conversion right here. Okay. Use that relationship to do all of our conversions here. Okay. I'm going to put the 180 degrees in the denominator and the pi radians in the numerator. Now, why did I do that? Well, because when you have two fractions that you're multiplying together here, right, the numerator unit, to get it to cancel out, I want to put the same denominator unit. Okay, so I have my numerator unit here of degrees. I need to put my degrees in the denominator then, so that way my units will cancel. Okay, and now when I multiply, I will have 47 times pi, and that will be now in radians. And then 1 times 180. The degrees canceled, so I'm left with just radians here in the end. And that's my unit of measure. Okay, so 47 pi over 180, that is the number of radians. Okay, as a decimal, okay, as a decimal if you're curious here, okay, hit enter. All right, 0.820, okay, so it's like just less than 1 radius, right, just less than 1 radius around the circle. So like if we go back to those circles we were looking at earlier, okay, 47 degrees would be, well, there's 1 radius, so 47 degrees would be like somewhere here. Okay, we create this angle right here. Okay, because that's 1 full radius, and the radian measure is 0.82, so like just a little bit less than that, you know, kind of thing, and that would create that angle right there. Okay, 47 degrees. All right, let's do another one. Let's do something more familiar though. Let's do like 150 degrees, and we're going to convert that from degrees to radians as well. All right, so I'll put it over 1, and I'll multiply by, well, again, I want my degrees to cancel, so I'll put that 180 degrees in the denominator, and then pi radians in the numerator. Okay, degree units will cancel. 150 times pi, 150 pi, over, and then 180 degrees, like that. Or not degrees, sorry, just 180 because the degrees canceled. Okay, now there's my number of radians. Now, what can we still do here, though, that we couldn't do up here? Right, what can we do with this fraction here? Yeah, it simplifies, yeah. So we'll divide by 10, we're left with 15 and 18, right? But 15 and 18 also simplify. What do 15 and 18, what can we divide out of 15 and 18? A 3, right? And it becomes 5 over 6, exactly right. So yeah, this is really 5 pi over 6 radians. Okay, now remember, what was pi over 6 radians? We said it earlier. What's pi over 6 radians? 30 degrees, right? Well, 5 pi over 6. What's 5 times 30? What's 5 times 30? 150. Hey, look at that. Okay? So 1 pi over 6 was 30 degrees. 5 of those pi over 6s, right? 5 of the pi over 6s ends up with 150, which is 5 times 30. Okay? So you can, use that kind of math to help you, kind of work see your way around and stuff like that too. All right, let me have you guys try one here. All right, so how about you guys try 300 degrees, and I want you to convert that into radians. Okay, so go ahead and give that a try. I got my 2 examples up there. Okay. Once we do that, we'll talk about radians to degrees. We'll convert backwards too. Okay. And then we'll finish up our talk about trigonometry and right triangles and stuff. Yeah, go ahead. Solid. I think I'm also going to continue to allow you guys, so of course we will have a quiz, we will have a test and stuff like that. I'm definitely going to continue to allow you guys to use your notes on the quizzes if you want. So, you know, make sure you're taking good notes here too, because that'll help you with when it comes to quiz time, all right? I think I'm going to continue to allow you to use your notes on quizzes if you want, all right? You don't have to, of course. Extra challenge. Yeah. Yeah. Mm-hmm. Almost tripped there. Yes, and you can simplify one more, right? Because 10 and 6 both are even. But yeah, you're on the right track. Good job. Okay. So hopefully you now multiply by pi over 180 degrees. Okay, again, why do we do pi over 180? Because 180 and pi, they are equivalent, right? We already figured that out, right? You could use 360 and 2 pi if you want to. I like the 180 and pi, though, because, well, anything less, and you're going to have fractions, and anything more, and it might simplify. So I think 180 degrees in pi is the best kind of, like, conversion that you can use. Okay, so we use the equal radian and degree measures here in the ratio, or not, I guess not a ratio, in the fraction there. But we put the degree measure in the bottom so that way the degree measure in the top will cancel, right? And so we end up with 300 pi over 180. But we really should not be satisfied with that because 300 and 180 simplify, right? And what does this eventually simplify to be? 5 pi over 3, okay? And if you think about, and again, I just happened to pick two things that are 5 pi over 3. But if you think about this, right, well, we knew pi over 3 was 60. Oops, sorry, let me scoot back out here. We knew pi over 3 was 60 degrees, right? 300, well, that's just 60 times 5, right? 300 is 60 times 5. And so when I take pi over 3 and I multiply by 5, I get 5 pi over 3. And so they're equivalent still, right? All right. Let me do one more conversion here. I'll do like a radian measure. So let's say I've got, for example, 11 pi over 6. Okay, 11 pi over 6. Now, again, some of you might be able to tell what this is going to be. Let me block off here. What do we know pi over 6 is as a degree measure? 30. And so then 11 pi over 6 is just going to be 30 times 11. So we should end up with what here? 330 degrees. All right, let's see what happens. So I'm going to put this all over 1. I'm going to multiply here. Now in this case, I have a radian measure in my numerator. So when I go to multiply here, I'm not going to put the 180 in the denominator. I'm going to put the pi in the denominator because it's in radians, and the radians measure will cancel out. And I'm going to put the equivalent degree measure on top. Okay? So again, because we're dealing with radians here, I have to put an equivalent radian. I have to put the radian measure in the bottom and then the equivalent degree measure on top there to cancel. Okay. All right. So we're going to multiply this. Now this is where it gets a little bit tricky because I have to do like 11/6 times 180. Okay. Well, the pi's are going to cancel, right? I mean, clearly we can see the pi's will cancel, so that's easy. And then we just got to do 11/6 times 180. Well, go ahead and do it in your calculator, and you're going to get 330 degrees. Okay. If you don't believe me, I will show you. Oops. There you go, 330 degrees. Okay? Easy peasy. All right, so questions on any of that? That's how we convert. All right. So that's what we're going to, so that'll cover us right now for radians and degree measure stuff. We're going to get more into this as we go, so this is not the last. We're going to see it. In fact, we're going to be getting more fluent with these radians too. So just as comfortable as you feel with degrees, we're going to get that comfortable with radians as well, hopefully. That's the ultimate goal. Okay? And then I think eventually I would like us to be able to get to the point where we can do graphs like... I'd like us to be able to eventually get to the point where we can do graphs like this. I think. Okay? So... I will have to show you. We'll have to. It's going to take a little while to get to this point, but I think we should be able to get to this point. And I think I want to do that. So we'll see here. Okay, but it's a different kind of like graphing system. So anyway, we'll hopefully get to that point eventually. Okay, I think we should have enough time though. I think it's neat enough to go to. Okay, so that's that. Then let me do my quick trigonometry review. Okay, again, I know we already kind of covered some of this yesterday, so please forgive me for repeating myself in some situations, but you know, I just want to make sure we're all good here. We're all squared away. Okay. And I think I might even draw the same thing I drew yesterday. So I'll draw a right triangle here. I've changed where I put my A, B, and C though, so sorry if that's going to frustrate some of y'all. Okay. Typically the way that we label our triangle, right, we use capital letter for angles, lowercase opposite side, lowercase letter version. Okay, so if this is angle A, then opposite that should be little a. This is angle B, opposite that should be little side b, and opposite angle C should be side C, lowercase c. Okay, and so we'll have our different trig ratios here. I'm going to put theta in here too. Okay, and let's redo sine theta, cosine theta, tangent theta again. So what would sine of theta be here in this case? Opposite of hypotenuse. So in this case, that would be what over what? Yes, A over C. Good. What about cosine? What would that be in this case? Adjacent. What's the adjacent leg to theta? B over, then what's the hypotenuse again? C. Okay. And how a tangent of theta? Yeah. Over adjacent leg. Yep, that's right. Remember we use so, ka, toa, right? Make sure you spell it correctly. I failed a quiz in my geometry class once because I spelled it so, ka, tau, T-A-O. And that messed up enough problems where I failed it. So, womp womp. So, ka, toa. So, ka, toa. Okay, it sounds like something you chant around a fire or something like that, you know? Some sort of pagan ritual. Don't do that. All right, now, how about cosecant of theta, secant of theta, and cotangent of theta? You guys ever seen those before? No. Right, exactly, CJ, exactly. You never seen cosecant, secant, or cotangent? Has anyone ever seen these before? Yeah. Yes. Oh, okay. Where'd you see it? What class? Yeah? So cosecant is really just 1 over the sine of theta, which when we have 1 over, that just means the reciprocal, right? So what's the reciprocal of sine of theta in this case? C over A. Yeah, exactly right. Okay, and then reciprocal of secant. So a secant is reciprocal of cosine. This is like, to me, one of the dumbest things that I ever teach. Okay? You guys might think, Mr. Wood, there's a lot of dumb things you teach. All right, that's your opinion. But my point here is that, like, why would you ever have cosine and then its reciprocal be secant when you have sine's reciprocal be cosecant? Like, why couldn't you just say cosine's reciprocal is cosecant and sine's reciprocal is secant?
Is that
S-C-S-C-S-E-C-C-O-T. Okay, sorry, I guess I should write that out. Yeah, this is cosecant, secant, cotangent. Okay, and I'm sure there's a reason for it. I tried to look it up, though, but I didn't get much help. But anyway, okay, it just seems like a dumb naming thing. Cotangent and tangent, that makes sense, right? And that's exactly what it is. 1 over tangent is cotangent. And so that would be B over A, and this is C over B. Okay? If you take all of these and like do the, so in other words, cosecant is hypotenuse over opposite. So basically it's like this. Choshikaw. Okay? So you have so ka toa, you have cho sha cow. Okay, you really don't need to remember that though. If you remember these, then you just flip them, right? You just have to remember that sine and is reciprocal to cosecant and cosine is reciprocal to secant. You don't really need to remember Choshikow, but it's a fun word to say, in my opinion. Okay, and again, what's the point? What's the point of all these six tricks? There's no more, but there's beyond these, so you don't have to worry about that. What's the point of all these things? Why do we need them? Well, sometimes, right, we want to relate an angle in a right triangle with sides. All right, sometimes we want to relate angles and sides. Okay, if we want to just relate the sides of a right triangle, we have the what theorem? What theorem relates the sides of a right triangle? What theorem relates all three sides of a right triangle? Pythagorean theorem. That's right. Okay, but when we want to relate angles and sides, then we want to use these trig ratios. Okay, super helpful. All right. So just a quick example here. We'll just do one. All right. So let's find the 6 trig functions for theta. Okay. So I'll just draw a little triangle here. All right, so let's go ahead and do this. We'll do sine of theta, cosine of theta, tangent of theta first. Okay, and feel free to use your SOHCAHTOA if you need to help you out there. Okay, so sine of theta, what's that going to be here according to my triangle that I've drawn? Sine of theta will equal what over what? Okay, and what is the opposite and the hypotenuse here? What's opposite from angle theta here? 12 over the hypotenuse of, so leave it blank. No. What should we do? Find it. How? Use the angles?
No. You use like sine or tangent.
We only know the 90-degree angle though. That's it, and we never really use sine, cosine, tangent with a 90-degree angle. We have two sides of the right triangle, and we need to.
45 degrees.
Is it 45 degrees?
I mean, I don't really.
We don't know that. That's okay. You just said it though, Cheyenne, earlier. I mean, not like the last thing you just said, but like some of the earlier things that you said. Like if we have two sides of a right triangle, we want to find the missing third side. What relates all the sides of a right triangle again?
90.
What theorem? Pythagorean theorem. That's right. So we're just going to solve for it here real quick. Leg squared plus leg squared equals hypotenuse squared. Right? Leg squared plus leg squared equals hypotenuse squared. 5 squared is 25. 12 squared is 144. 25 plus 144? 169. And what is the square root of 169? 13. Nice, easy number there. Okay? Now technically, I'm in an equation setting here, right? When I square root both sides in an equation setting, I'm supposed to put a plus or minus. But why don't I put the plus? What's that? 13 is a perfect number, you're right. There's no decimals after it, but why did I just leave it positive though? Why didn't I say plus or minus 13 here? CJ. It doesn't make sense in the context, right? A negative 13 would not make sense in the context. You take out the context and you just have, like if you're just solving this equation, take out the context, you're just solving the equation, 13 and negative 13 would be answers. But we're talking about a triangle's length, you won't have a negative 13 side length. Okay, sorry.
What is that? 2 in parentheses? That
it's c squared, yeah, square root of c squared, and then 169 there. So, okay. Now, just as a little side note here, when you have all three sides that are nice numbers, Pythagorean triple is what that's called. Does anyone know another Pythagorean triple that's really nice? The simple one is 3, 4, 5. 3, 4, 5, that's the easy one. 3 squared plus 4 squared is 5 squared. So 3, 4, 5 is the easiest one. But this is another Pythagorean triple. Okay, there's, I think, an infinite number of these. I'm not sure if that's been proved or not yet, though. Okay, anyway. So cosine of theta, what would that be then? Oh, sorry, it's 12 over 13 there. There we go. So now cosine of theta would be what? Cosine is adjacent over hypotenuse. So cosine would be, what would it be in this case? What's adjacent to theta? 5. Sorry, Jason, you're probably going to hear your name sound like adjacent. So, and then over 13. That's right. All right. And then tangent of theta? Opposite over adjacent. 12 over 5. All right, now let's do our other ones real quick. This will be super easy because we just did. Oops. Man. Engage brain here. Here we go. Okay. All right, cosecant. What would that be? If sine's 12 over 13, cosecant will be 13 over 12. Yeah, just reciprocate it. Okay. If cosine's 5/13, secant will be 13/5. You got it. And then cotangent will be 5/12. Exactly right. Okay. Easy peasy. Easy peasy. Okay. I also want to briefly mention, so that's, that's setting them up, right? We're not actually solving anything here. We're just kind of setting up the relationships, and then we'll eventually use this to solve it. In fact, we'll get to that in just a second here. I got one other little thing I want to show, though, too. The special right triangles. Remember those? So we have some special right triangles. You guys remember your special right triangles? We have 2 of them. Something, something, 90, and something, something, 90. Okay, that's one of them. 45, 45, 90. Let's do that one first. Okay, so I'll draw that. Okay, so like good geometry memories, right? Or we can also call it the pi over 4, pi over 4, pi over 2 triangle, right, if we want to use radians. Yes, 30, 60, 90 is the other special right triangle that we're going to worry about. There's only 2. Okay. So, obviously we're talking right triangles, right, special right triangles, but since this has a 45 and a 45 degree angle here, what do we know about these 2 legs? They're going to be what? Equal, right? Because they both have those same angles there. So we'll say x and x. What do you call a triangle when you have 2 equal sides? Starts with an I. Isosceles. You got it. Isosceles. Okay. The hypotenuse. So this is an isosceles right triangle. Okay. The hypotenuse here, okay, is going to be x times the square root of 2. That actually comes directly from the Pythagorean theorem, right? If you do x squared plus x squared, you're going to get 2x squared. You square root both sides, you'll have x times the square root of 2 then for your missing third side there. You guys remember like solving for different pieces? Like maybe you were given the hypotenuse and you had to come up with what the legs were, or maybe you were given a leg and you had to come up with the other sides when we're doing that kind of thing? Yes, you do. Good. Okay, it was fun. All right, and then the 30, 60, 90. Or the pi over 6, pi over 3, 90. Or pi over 6, pi over 3, pi over 2 triangle. Okay, you remember the relationships here? The short leg was, okay, if you don't remember, that's fine too. X. The hypotenuse is twice x. And then you remember what this third one is? I know, it's been too long. X square root of 3 in this case. 3. Okay. we bother learning these triangles because you can actually like derive where both of these come from, right? So like I said here, this one we can come up with this relationship pretty easily because it's an isosceles, so the two legs are going to be equal, and then you can use Pythagorean theorem to come up with that third side. So that's why we kind of like bother learning this special right triangle, right? Why we even bother with it. Same thing here, or similarly here, this is half of an equilateral triangle, right? If you were like to imagine here, I could like, you know, create that equilateral triangle here, and then if I like were to cut it in half, there's the 30, 60, 90, right, triangle that we talk about there. And so because, again, the triangle is equilateral, you know, if each side is 2x, then that would mean this is just x, and then we can use Pythagorean theorem again to get this third missing leg right there. Okay? And so that's why I think we bother learning about these special right triangles, because you can come up with these nice relationships without having to, like, do other weird stuff, I guess. Okay. Okay, last little thing here. So we'll come back to that later. All right? I just wanted to briefly talk about solving right triangles. Okay, again, this is just supposed to be a refresher, so I won't go into like too much depth here, but let's just do one example. Solve triangle ABC. And let's say that I've got sure. If you're feeling okay on this stuff, go ahead. Okay. So let's say we're going to solve this right triangle. What do I mean by solve triangle ABC? What do you think I mean by that? Find all the angles. Find all the sides. Exactly right. We're going to find all the missing pieces here. Okay? All the missing pieces. All right. You guys remember how to do that? We've got an angle. And what is this side in relationship to this angle here? Opposite, adjacent, or hypotenuse? What is B in relationship to that 28 degrees? Is it the opposite leg, the adjacent leg, or the hypotenuse of the triangle? The adjacent leg, right? It's right next to it there. Okay? So, what trig ratios, right? If we have an angle and a side, we need to use a trig ratio here because that's what we use to relate sides and angles, right? What trig ratios have adjacent in them? Okay, let's use cosine. You said that one first. So cosine of what angle are we going to use here? Yeah, 28 degrees or angle A. So we'll use 28 degrees there because we actually have a number. Equals, cosine is what over what? It's the ka, right, of SOHCAHTOA. So it's, adjacent over hypotenuse. So the adjacent leg, which is 15, over the hypotenuse of C. Okay? And so we're going to be able to use cosine here to solve for the hypotenuse because we have this, there's our variable, right? One variable in this equation here. How can I get C out of the denominator here? What can I do to both sides to get C out of that denominator? We're going to multiply both sides by C. Okay? And then I'll have C times the cosine of 28 degrees equals 15. And then how can I get the C by itself now? What do I need to do to both sides here? Not subtract. We have multiplication here, right? So we're going to divide. Yeah, divide both sides by cosine 28 degrees. Okay, cosines cancel. You're left with C equals, and then let's go ahead and type that in your calculator. 15 divided by cosine 28. Make sure I'm in the right mode here too. Okay, I get about 16.988. So I'm just going to go ahead and round that up to 17. Okay. 28 degrees, the angle. You do cosine of your angle equals the adjacent leg, 15, over the hypotenuse, unknown C. Okay, it just came, that was given to us. The 28 degrees was given to us in the picture. Okay, so C is about 17. Okay. What other trig ratio could we have used here? So cosine had adjacent in it. What other trig ratio has adjacent in it? Tangent. So we also could have said tangent of 28 degrees is equal to, now tangent is opposite, so it'd be A over 15, A over B, which is A over 15. And we solve in a similar fashion here, but now I just need to multiply both sides by 15. Okay, and so I get A equals 15 times the tangent of 28 degrees, which is about 7.97, so I'll say it's about 8.0 there. Okay. Have we solved the triangle yet? There's one more piece that's missing. Angle B. But how can you find angle B?
Divide angle.
What do all the angles in a triangle have to add up to be?
180.
180, right. And so, like you were saying there, Tatum, yeah, these two angles, the two acute angles, are going to add up to 9 degrees. So these are going to be complementary, right? A and B are complementary. Okay. So it's going to be, let's see here, 28. So angle B equals, 180 degrees minus 90 degrees minus the 28 degrees, which is equal to 62. Okay, so there's all of our pieces. Well, okay, there's all 6 pieces there. Yep. Yes, go ahead. In fact, I think I'm going to go ahead and get you guys started on your assignment here too. Okie dokie. So, I'm going to give you kind of like a 2-parter here for your assignment because we did kind of cover 2 things. All right. You're going to go back into 17.1, the stuff that we did. Stuff that we did yesterday a little bit here. Okay. So homework, and yes, I'm trying to give you some time to work on it here in class. So 17.1, which I forget what that page number was now. Shoot.
That was 605.
Okay, 605. Thank you. Okay, starting on page 605 there. So it was. 605, I'm going to have you guys do numbers 7 to 7, and let's just have you do 7 and 13, I think. Right
Just
there.
those 2?
I think I'm going to add on a little bit here. I know, Patrick, I know. Everyone's like, wait, Patrick, don't ask for more. But no, I'm going to give you a few more here, yes. Okay, I'm also going to give you something from, I don't know, what can I call this? How can I make this easy to identify? So like, it's going to be in a PDF online here, okay? Because I don't have enough green books unless everyone wants to take a picture or something like that. So PDF, I'm going to have you numbers, bless you, numbers, 3, 9, and we'll just do like 21. I think that should be okay. Okay, and I'll scan these here for you guys to see. Okay, so I'm gonna put this. I'm gonna scan these because it's from a different book. It's this green book here. Okay, it's like the old Algebra 2 book that we used to use. So anyway, there's your homework. You got those 2 questions there. You can at least start working on, and then I'll quickly scan this and put it up on the Google Classroom so you can then see, get that done too. Okay. Try not to give you a lot, but I do want to give you just a little bit here.
So like